So when we are row reducing a matrix, we need to know what the end game is. We need to know when can we stop the row reduction? When have we done enough? And we know we've done enough if we get the matrix in a particular form, and we call it reduced row echelon form, or for short, we use RREF. So a matrix is in RREF if it satisfies the following conditions, and there's 4 conditions. First condition is all rows that contain all 0 entries must be below all rows that contain non-zero entries, meaning that if you get any row of zeros, you've got to move it to the bottom of the matrix. If you have 2 rows of zeros, then those 2 rows need to be the last 2 rows. Second, from left to right in every row, the first non-zero entry must be a 1. So if you're reading a row from left to right, the first non-zero number that you get must be a 1, and we call this a leading 1. And third, from top to bottom, each leading 1 must be below and to the right of any previous leading 1, meaning your leading 1s have to be staggered down the matrix. And the staggering is where we get the echelon name. Echelon is kind of a military term where you march your troops in a staggered formation, so they call it echelon. And fourth, if a column contains a leading 1, then each entry in that column that's not the leading 1 must be a 0. So this is the elimination part that we talked about in Gaussian elimination, where we have to eliminate those entries in the columns. We have to make them zeros. So if you have a leading 1 in a column, then you've got to use that leading 1 to eliminate all the other entries in that column. So I have some examples of matrices, and we're just going to decide if these are in RREF. Are they in reduced row echelon form? So the first matrix is kind of our ideal goal. We want to get, if we can get it in this form, then we're happy. So let's just go through the 4 requirements. This does not have a row of zeros, so we can skip that part. If we read from left to right, the first non-zero entry in each row is a 1. Right? The first time we get to a non-zero number, that is a 1. And these 1s here are called leading 1s. They lead the row. They're the first non-zero entries. The leading 1s are also staggered. The next leading 1 is below and to the right of the previous leading 1, and the next leading 1 is below and to the right of the preceding 2 leading 1s. So we have that echelon form. And last, in a column that contains a leading 1, the other entries are zeros. And that's true here as well, right? In all 3 columns, we have leading 1s, and every other entry in the column that's not the leading 1 is a 0. So all this checks out. This first matrix is in RREF. This is reduced row echelon form. So for the second one, we can tell right away it's not in RREF because I have a leading 1 in this column, and I have an entry that's not 0 in that column. So we would want to eliminate this entry and also these 2. We want to make those zeros as well in order to get this into reduced row echelon form. The form that this is in, it's that triangular form that we talked about, and in fact it has a special name that's very similar. It's just called row echelon form. it's got the staggered ones, it's got the leading ones in the rows, all the, if it had rows of zeros, they'd be at the bottom. Okay. It has all the stuff that reduced row echelon has, except it doesn't have all these members of the columns with leading ones turned to zero. So it's not reduced completely, but it does have that echelon formation about it. So it's called row echelon form, or REF. Okay. So the next one is interesting, right? So we do have a row of zeros, and it is at the bottom. We have these leading ones that they're the first non-zero entries in those rows. The last row doesn't have a leading one, but there's also no other non-zero entry, so there is no non-zero entry, so that's okay. And there's only 3 columns that have leading ones, and in those 3 columns, all the other entries in the columns are zeros. So this one satisfies RREF as well. This is in reduced row echelon form. Yes, we have this 2 in here, but its column does not contain a leading 1, so we really can't do anything with the 2. Okay, we can't get rid of that 2. So this is, in fact, in RREF. I got too many R's. Well, I don't know what I'm doing there. RREF. So the last matrix looks like the first matrix, except it's got this extra column, and it looks like it's one of those augmented matrices, right? So this might be a system. Doesn't have to be, but it might be. And we do have the leading ones, right? So every row, the first non-zero number is a 1. Every other entry in those columns is 0, and there's no row of zeros. This column does not have a leading 1, so we don't worry about if those entries are zeros or not. We just want to eliminate the other column members in the columns that have leading ones. So this guy is in RREF. So all of these are in RREF except this one, which is just in REF, or what we call row echelon form. In some books, it'll just say echelon form instead of row echelon form. So each matrix can be reduced to 1 and only 1 reduced row echelon form. So once you get to reduced row echelon form, you can't go any further. You can't reduce it any further. And that matrix is the reduced row echelon form, the only reduced row echelon form for the original matrix. Now, different matrices can be reduced to the same reduced row echelon form matrix, but each matrix has only one reduced row echelon form. You can't reduce it to 2 different ones, okay? And an entry that has a leading 1, we call that a pivot entry. And a column that contains a leading 1, we call that a pivot column. And those are going to be important terms later on. So we're going to row reduce this matrix, and we're going to identify the pivot entries and the pivot columns. So I'm going to do this by hand, and then maybe I'll show you the calculator, and after we do it by hand, I'll show you how to do it in the calculator. So first step is I want to have a 1 in the top left corner. So I'm going to switch it with the third row. So let's say switch row 1 and row 3. I like row 3 because all of these are divisible by 3, right? So when I divide this by 3 to make it a 1, it's going to be nice. Okay. So put row 3 first. I didn't do anything to row 2. And move row 1 to row 3 spot. Now, it didn't tell me this was an augmented matrix or this is a system. It's just a matrix. So we're not worried about solving a system here. Now, we might look at that after we're done, but, you know, matrices don't have to be systems. So now I'm going to, let's do this first. How about we take row 2 and subtract row 1. So row 1's already a 3. And I'm going to make this a 1 eventually, but it's already a 3 and this is a 3. So if I subtract those, I'll get the 0 right here that I want. So I'm just going to take row 2 and subtract row 1. And how about we go ahead and divide row 1 by 3 next. So I'll replace row 1 with 1/3 row 1. So let me write down the third row. And the first row is going to be row 2, or sorry, let's do the second row. Second row is going to be row 2 minus row 1. So 3 minus 3 is 0. -7 plus 9 be positive 2. 8 minus 12, -4. -5 plus 9, that's going to be positive 4. 8 minus 6 is positive 2. 9 minus 15 is -6. And then I'm going to divide row 1 by 3. 1, -3, 4, -3, 2, and 5. So now I've got my first column done. I've got a 1 and all the other entries in that column are 0. So the next step is to make this guy a leading 1, right? It's the first non-zero entry. I want to change it to a 1. So I'm going to replace row 2 with 1/2 row 2. I'm going to write down the other rows. I'm going to divide this by 2. And now I've got a 1. So I'm going to use this 1 to eliminate the other entries in that column. And when you do this, it's called pivoting. So, you know, we call this a pivot entry, you know, when we pivot there. And we're going to call the column a pivot column. The act of pivoting is taking that leading 1 and using it to eliminate the other members of the column. So row 1, we're going to replace with row 1. You know, we could actually add row 3 and do it, but let's just use the 1 here. Let's actually do the pivoting. Row 1 plus 3 row 2. And then we need to change row 3. Row 3 minus 3 row 2. What you can't do with row 3 is add row 1. So I could take row 1 and change it by adding row 3. That'll give me the 0 here. The 0 in row 3 will not change the 1 in the top left corner that I want. But if I take row 1 and add it to row 3, I will add this 1 to the 0 and I'll create a 1 in this position. I don't want that. I don't want to mess up my zeros in the first column. So if you only pivot, you know, you'll avoid that issue because you've already fixed this column. You're not going to mess up anything else because you've got a 0 entry before this. All right, so now let's do those operations. I'm not changing row 2. So for row 1, I'm adding 3 row 2, so it's going to be 1 plus 0. Negative 3 plus 3 is 0. 4 minus 6, negative 2. Negative 3 plus 6, positive 3. 2 plus 3 is 5. 5 minus 9 is negative 4. And then row 3, we're going to subtract 3 row 2, 0 minus 0, 0. 3 minus 3 is 0. That's what I wanted. Negative 6 plus 6, that's going to be a 0. 6 minus 6, right? 6 minus 3 times 2, that's a 0. 4 minus 3 is a 1. And negative 5 plus 9 is a positive 4. So that's interesting. So we ended up with 4 zeros. I thought we might get a whole row of zeros, but we didn't. And I've got a leading 1 here, leading 1 here, and in the third column, the leading 1 doesn't come until the fourth column. So we're still going to pivot. We've got to make these entries 0. So I've got to change row 1 and row 2, and I'm going to use row 3 to do it. So for row 1, I'm going to say row 1 minus 5 row 3. That'll make this a negative 5. We add it to this, it'll make it a 0. And then for row 2, I just need to straight up, I just need to subtract row 3. Because that's already a 1, so just be 1 minus 1. So the last row does not change. First row, row 1 minus 5, row 3. The first 4 entries, I'm just subtracting 0, so those will stay the same. And then 5 minus 5 is 0. And then I've got negative 4 minus 20, right? Negative 5 times 4. Negative 4 minus 20 is going to be negative 24. And so that's row 1. So now row 2, again, when we subtract these zeros, nothing will change. And here I have 1 minus 1, and negative 3 minus 4 will be negative 7. So we have our leading ones in every row. Every entry in those columns with the leading ones are 0. So this is in our Rref, and I don't have a row of zeros, right? So it asks me to identify the pivot entries in the pivot columns. So now, the pivot entries are here, here, and here. That is where we pivoted. That is where the leading ones are. And the pivot columns are the first, the second, and the fifth columns. So first column, second column, and fifth column are the pivot columns. And these, where these leading ones are, those are the pivot entries. That's where we pivoted. Okay, so let's do this in the calculator and see what we get. And then, see if we get the same thing. And we will also talk about this. What if this was a system? What would the solutions look like? So in the calculator, you have a matrix button, and you need to use the second key to get matrix. You need to scroll over to edit. We want to enter our matrix in. And right now it's 3 by 4. But what is this matrix? It's 1, 2, 3 rows and 1, 2, 3, 4, 5, 6 columns. So when you're talking about the size of a matrix, it's always the number of rows first and the number of columns second. So this is going to be 3 by 6. And then I'm going to enter in the entries. I'll press enter each time. And if you have a negative number, you have to use the negative symbol and not the subtraction symbol. Subtraction will confuse the computer. It thinks you're subtracting two numbers instead of just declaring a number a negative. So I'll just try to do this quickly. Whoops. Every time you do this, you'll want to go back and check just to make sure that you entered everything in correctly, because this is tedious and it's easy to mess up, especially a sign. It's easy to mess up the sign. All right, so I'm just going to scroll through here. I like to do this by column. 0, 3, 3, 3, negative 7, negative 9, negative 6, 8, 12, 6, negative 5, negative 9, 4, 8, 6, and negative 5, 9, and 15. All right, so this is matrix A. So now we're going to quit. So I'm going to do second mode quit. This brings you back to the calculation screen, and we're going to do the calculation. I'm going to go back to the matrix menu. So second matrix, and go to math. And I'm going to scroll down until I get to Rref, reduce row echelon form. And I'm going to enter in A, and you go back to the matrix menu under names and just declare A as your choice and hit enter, and it will reduce the matrix. And we're just going to check our answer here. It looks like we did it correctly. Okay. Now, I think you should really learn how to row reduce by hand before you start just using the calculator. But it's going to be a lot of problems later on where using the calculator will help you with time, because you're probably not going to have enough time to do everything in the calculator. Okay, so we'll use the calculator a lot more, but I think you need to spend time doing these by hand to start with. All right, so let's look at this as if it were a system. And what would the solutions be? So if it's a system, it's augmented here. And we have these variables, right? So these columns would be variables, x1, x2, x3, x4, and x5. So our solution has got to be in this form, x1, x2, x3, x4, and x5. And the columns that have leading ones are basic, and the ones that don't have leading ones are free. So x3 and x4 are free. I'm just going to write x3 for x3 and x4 for x4. So now we're going to write the basic variables in terms of the free variables. And the easiest one to start with is x5. x5 just says x5 is equal to 4. So we can just write down 4. x1 and x2 have coefficients of x3 and x4. So what we want to do is we want to move these to the right side of the equation symbol. Remember, this line, this augmentation line, is like it's like acting as the equation symbol in these equations. So just for example, the first equation is x1 minus 2x3 plus 3x4 equals negative 24. And we just want to solve this for x1. So we would move the x3 and x4 to the right side. And that's what we're going to put here in our solution. We're going to do the same thing for x2, so I need to move these two coefficients to the right. So that's going to be positive 2 x3 minus 2x4 minus 7. So this would be our solution to this system, if it's a system.